Let's discuss some aspects of interpreting Ampere's law. Suppose we have four wires here seen in cross section coming out of the page like that. These two wires are carrying currents into the page, 5 amps and 3 amps, and these two wires are carrying currents out of the page. So Ampere's law will help us relate the magnetic fields produced by all of these wires in the surrounding regions to the currents being carried by those wires. And we use it by imagining paths, sort of loops that we can draw in the environment. So one possible path that we could draw would be to sort of draw a loop like this that encloses some of those wires, but say leaves this one over here out. So we have a path here, like a hike, and this is just a one-dimensional loop here. We're not imagining any kind of 3D Gaussian surface in this case. Just a loop, a path, and we imagine also a direction of hiking around that path. Let's say we move in this direction around that path. So at any given point on the path, you could draw in a little tangential displacement vector, ds, your little step forward, one step forward along that path, tangent to the path. Here are all our little displacement vectors, little ds's, going all the way around. Okay, we have enclosed some current in this path, meaning if we imagine that this path is kind of like a boundary, then the surface bounded by that path is being penetrated by these three wires. So we've got some currents coming in and out of that surface through these three wires. This wire is not enclosed by the path, so the current from this wire won't be included in the current enclosed here. Okay, let's call this path number 1, and over here write a statement of Ampere's law for that path. So in the closed path integral, b dot ds around path 1, right here, say path 1, that'll equal our constant mu naught times the current enclosed inside that path. Okay, so I've got these three wires. We have to decide on the signs of these currents, which ones are positive and which ones are negative. And we determine that by relating the direction of travel around the path to the direction of a positive current using another application of a right-hand rule. So take your right hand, place it on the page, and allow your fingertips to curl in the direction of travel around the path. So we're going in kind of a counterclockwise direction around this whole path here. And if I do that, my thumb on my right hand points straight up. That indicates that straight up will be the direction of positive current, must be the direction of positive current. I'm saying here, we're using a right-hand rule to make the direction of integration, that's this counterclockwise direction of travel around the path, we make that direction of integration sort of agree with the direction of positive current. So if we're going to go counterclockwise around this path, then out of the page has to be the direction for positive current. So this 7 amps represents a positive 7 amps penetrating through that bounded surface, and these 5 amps and 3 amps represent negative 5 amps and negative 3 amps penetrating in through that bounded surface. So our total current enclosed would be the -5, -3, and +7 amps. So that's -8 plus 7, a total of -1 amps would be the current enclosed by that particular path. Okay, let's draw a different path because we can draw any shaped path we like. So how about something like this instead? And around that path, we'll call it path 2, let's travel in kind of a clockwise direction instead. Let's imagine hiking this way around that path. So some of our little ds vectors, our little displacement vectors tangent to the path would be like this. let's set up Ampere's law for that path. So the B field.ds integrated around that closed loop equals mu naught times the current enclosed. Okay, now we need a right-hand rule again to compare the direction of integration to the direction of positive current. This time, if we're sort of moving clockwise around that path, then take your right hand, fingertips curling clockwise around the path, then your thumb will be pointing into the page. That means for this path, into the page will be the positive direction. So this wire right here, carrying current into the page, will represent a positive 3 amps. This wire, carrying current out of the page, will be a negative 7 amps. These two wires are not being enclosed by this particular path, so they don't contribute. So our current enclosed here is a negative, nope, this is into the page, so that's positive according to our right-hand rule. Positive 3 amps, that's a negative 7 amps. So our current enclosed is negative 4 amps by that path. Okay, here's one for you to try. I'm going to draw the path, then ask you to pause the video for a moment and determine the current enclosed by this path I'm about to draw. Okay, this one will be, say, like this. Let's make that path number 3. And suppose we'll travel in this direction around that path. Okay, pause the video for a moment and work out the current enclosed by path 3. Ready? Okay, if we're going this direction around that path, then that's kind of a clockwise travel. So by right-hand rule, into the page will be a positive current. So all currents into the page will be positive. So that's a positive 5 amps, a positive 3 amps for a total of 8, minus 7 amps for a total of plus 1 amps. This current is almost enclosed, but not quite enclosed by the path, so that one doesn't count. So plus 8 amps minus 7 amps, total of 1 amp positive enclosed by